All right, so we ended just talking about our normal lines coming in, or our light rays coming in parallel, hitting our mirror surface and reflecting based on your normal. That's right. So when we look at this, we get our spreading out of our light rays. I don't know if we talked about this yet, but when we talk about a mirror, does a mirror have to be glass?
No.
No. What could be defined as a mirror?
Satellite dish.
Satellite dish. What else? Water. Concrete. Chrome.
Metal.
Metal. Anything that reflects light, which means what? Everything that we can see could be considered a mirror. Okay? Because all we're talking about are objects that reflect light. But specifically when we're talking about, plane mirrors, that's when we're talking about glass or really smooth metals that can create a perfect reflection. So in this case, what type of lens is this, by the way? Convex lens, that's right. All right, so that finishes our reflection. Now we're moving on to refraction. So now we can start talking about lenses. So when we're talking about refraction, what is another term for refraction? What is happening to our light here? It's bending. Okay? So bending of light, and this is showing our different frequencies, our colors, and how much they bend. So which color is our frequency?
Blue.
No, red and blue.
I think it's purple.
Bless you. Well, if we're talking about which color bends the most, what would we say?
Pink. Oh, pink.
Bends the most
Pink.
are purples, or blues. Okay? Which one has that high frequency? So we're going to go back to our Snell's law. Snell came up with another equation. What was the first equation from Snell? C divided by V, right? Our optical density equals speed of light divided by our velocity through an object, or substance. Well, Snell's law also can calculate how much an object bends using this equation. What does our N stand for? Our optical density.
Yeah.
What does our I stand for? Incident. Then we have theta, which is our angle of incident, equals the optical density. R, what does R stand for? Refraction times the sine of our angle of refraction. As we are using this equation, obviously we're going to have to use our sine function on our calculator, but we'll go into more of that when we do some practice problems. So let's talk about diffraction. What is this dashed line? The normal. So say this material on the right side here, this rectangle, is glass. And the surrounding, the rest of this is air. Now, using Snell's previous equation, you calculate the velocity of light traveling through air and traveling through glass, right? So you know what the velocity, or how much the velocity changes. Well, what does that actually mean as far as the light bending? Well, say we have an angle, a light ray that is traveling at this angle. Remember, that's always in relationship to the normal. And then it's refracted when it hits the glass. So from this diagram, would you say it speeds up or slows down?
Slows down.
Well, we know when it hits something with greater density, it slows down, right? So let me ask you this. When light slows down, does the angle get larger or smaller in relationship to the normal? There's a diagram. Yeah. When it slows down, your angle becomes smaller. When it speeds up, your angle becomes greater. Now, if I wanted to, we could look up our velocity from our table, right, from optical density table, and label what these velocities would be. What would the air be? 3.00 times 10 to the 8 meters per second. What would glass be? 1.97 times 10 to the 8. Would you agree with that? Meters per second? Okay. All right. Now, what happens if we want to know what happens with light that goes from air over here in the left through? Say this is a window. Okay, we're magnifying. We're looking at a window. So then maybe this is outside sun ray coming, hitting the window pane, traveling through the window, and then coming the other side inside the house or building or wherever structure this is. So I have it labeled on top. I have on the left here low optical density, right? A high optical density in relationship to our low optical densities. So what's going to happen? Well, let's look at our light ray. So it's coming in at this angle, or incident angle. It's going to slow down, right? Because it goes through this higher density. And then what's it going to do on the other side? Speed back up. How fast is it going? Right here.
Yeah, 3.8.
in relationship to how fast it's going to begin with. The same speed. Okay? It's like going through slow motion here, lets you, and it's speeding back up. Now, why are there two normals? Where it enters an axis, that's right. Anytime that light travels through or changes a medium, if it breaks a barrier, you're going to need another normal perpendicular to that surface. What's important about these two? Or what's significant about our first ray and our third ray? They are parallel. That's right. So, the lower your density, the larger your angle. Does that make sense? Higher the density, the smaller your angle, because it's slowing down. Bless you. All right, this is our last push.
Ugh.
You ready?
Yes.
All right, so let's look at a practical application of this. We have a guy who's fishing, and he sees his fish. That's clear water. Means they're not in Oklahoma. And he sees this fish, so he throws his bait, looks like a worm, at the fish. Okay? Is that where the fish is?
No.
Where is the fish?
Higher up.
If light were to travel straight through both air and water, that's exactly where the fish would be, right? But that's our normal. What's going to happen right here when the light hits the water?
It's gonna bend.
Which direction?
It's gonna bend towards the
Left. I mean, right.
Going to a bigger angle or smaller angle? Smaller angle, so it's going to go down.
The fish is like really like right there.
So the actual fish is right there.
So if he's fishing and deceiving us for so long.
That's why, you know, the last time you went bow fishing, you were missing all your fish.
No.
Because when you're actually bow fishing, okay, you guys know what bow fishing is? You take a bow and arrow, and the arrow has a fishing line attached to it, and the reel is attached to the bow, and you shoot the fish with an arrow,
I don't do so.
and then reel in the fish. They do it with surface breathing fish like carp and gar. Anyway, whenever you are aiming for the fish, you have to make sure that you're actually aiming closer. You're actually aiming underneath the fish, right? Because the fish, that image is actually further away. Same thing if you, I mean, even a simpler example would be a straw in water, right? If you look at this straw in water, it looks like it's separated. because that light has bent it to look like the straw in the water is actually dislocated from the straw coming out of the water.
People starved before they realized they ate shit fish.
So here's our two lenses. We've already dealt with these in the lab. Which type of lens is this on the left? Concave. And which one's the one on the right? That's right. Concave and convex.
They're right next to each other.
Now, isn't this opposite from mirrors? What did a concave mirror do? It focused it in, remember? Satellite dish? And the mirror, the convex mirror, what did it do? It spread out the rays. Which of these is our eyeball? Convex. And I'll have a demo for you on Monday, which will illustrate how your eyeball works.
Look forward to it.